Practice 2.2, a study of elite distance runners found a mean body weight of 63.1 kilograms with a standard deviation of 4.8 kilograms. Part A, assuming that the distribution of weights is approximately normal, make an accurate sketch of the weight distribution with the horizontal axis marked in kilograms. So we want to draw our normal bell curve, and then we want to split it in half, and in the middle of our bell curve is 63.1, which is our mean. And then we want to fit 3 standard deviations to the right of our mean, and we want to fit 3 standard deviations to the left of our mean. So I would put one of your sections off in the end of your tail, and then you need to fit 2 more somewhat horizontally somewhat equal sections. And so 63.1, we're going to add 4.8 to figure out where our next place along our horizontal scale would be. So that would be at 67.9. We want to add 4.8 again. And so that gets us out to 72.7. And then we want to add 4.8 again. And that's 77.5. We want to do the same thing going to the left, but now we're going to subtract 4.8 from the mean. And again, we want to fit 3 equal spaces. I say equal spaces, but I just mean horizontally. You want to try to equally space them this way, is what I'm trying to say. So one there. So 63.1 minus the 4.8 gives us 58.3. And then we're going to subtract 4.8 again. And we've got 53.5. And then subtract 4.8 again. And we're at 48.7. So then the next question says, use the 68, 95, 99.7 rule to find the proportion of runners whose body weight is between 48.7 and 67.9 kilograms. So if you go 1 standard deviation on either side of the mean, so to the left and to the right, you have 68% of your data. If you go 2 standard deviations on either side, so 2 to the left, 2 to the right, then you have 95% of the data. And if you go 3 standard deviations, 3 to the left and 3 to the right, then you're going to have 99.7%, which is almost 100% of your data. So we need to use that information to figure out what percentage of the data, or what proportion of the data, is between 48.7, which is here, and 67.9, which is here. Okay, so we know that from here to here is 68. So one thing that tells me is that this is 34% and this is 34% because it's half of 68. Okay, then we know that the next standard deviation has 95% of the data between it. And so if I take the 95% and subtract the 68, then I'm left with 27 to be shared between these 2 little gaps right here. 27% of the data is right, or is shared between those 2, but it's symmetric. So if we divide it by 2, that tells us that each of these gaps is 13.5%. And then to get the next gap, I know that 99.7% of the data is from here to here. So that's going to be 99.7%. And so if I take the 99.7 and I subtract the 95, then it leaves me with 4.7 for those 2 gaps to share. So this little section here and this little section here, they need to share 4.7. So I want to divide that by 2, and that tells me that each one is 2.35%. Okay, and if you have 99.7%, and the whole curve is supposed to be 100%, then if we take 100% and we subtract the 99.7, that means that we're left with 0.3 for those tails outside of our 3 standard deviations. We're left with 0.3 for them to share. So if we divide that by 2, that tells us we have 0.15% in that side and we have 0.15% in that side. We didn't need all that information. We only really needed from here to here. So now we can add up all of our sections. But it's important for you guys to see where all the different percentages come from, because they may ask you about a different interval in another problem. So I'm just going to add up the 2.35 plus the 13.5. And I'm going to shorten a little bit and just go, okay, the next two sections together are 68. So add up that plus the 68. And so I get a total of 83.85. Okay, I know at this point we have learned to do normal CDF, and so a lot of us would just want to have the 48.7 be our lower bound, the 67.9 be our upper bound, 63.1 be the mean, 4.8 do the standard deviation, and try to get the answer that way. But since the problem specifically told you to use the 68, 95, 99.7 rule, which is our empirical rule, the answer we're going to get on the calculator is actually not acceptable. We can kind of check and make sure it's close to the same answer, but you'll see. I'm going to put it in for you. We're going to get a different answer, and we're not going to accept that as a correct answer. Okay, so by the normal CDF way, you get about 84.00 when you try to round that 2 decimal places. And so if you were to do that, it would be marked wrong because they specifically told us to use the empirical rule. From, the problems here on out, we can go ahead and use the normal CDF way of doing it. Okay. Part C, what proportion of runners have body weights below 60 kilograms? So I'm going to do the problems both doing the Z-score way because you need to practice that, but also just doing kind of the trick, throw it on the calculator and let the calculator deal with it for you. But please don't forget that you do have to know how to do a Z-score. So Z-score is, or Z is equal to observation minus mean over standard deviation. So that's going to let us solve for the Z-score. And so our observed mean is going to be, sorry guys, our observed score is going to be 60. The mean of our data is 63.1, and then the standard deviation of our data is 4.8. Okay, so I'm going to do alpha y equals to get my fraction button. And so we have 60 minus 63.1 on the top, 4.8 on the bottom. And that gives us a negative Z-score, which we would expect since we do have our observed score that is below the mean. So we have a Z-score of negative 0.14. I'm sorry. We have a Z-score of negative 0.6458. I was looking at something else. And then from there, we want to do the normal CDF of that. And we want to go below 60 kilograms. So normal CDF. And we're going to do to negative 10, because if we're going below, we're going all the way to negative infinity. So we're going to do negative 10 to an upper bound of negative 0.6458. We're going to leave 0 as our mean and 1 as our standard deviation because we're dealing with a Z-score. We're dealing with a standardized score. Okay, so we want to do second vars, number 2. Our lower bound is negative 10. Our upper bound is the Z-score negative 0.6458. I have 0 for my mean, 1 for my standard deviation because I want to be on the standardized normal curve. Okay, so that gives me a proportion of 0.2592. It's very common to go ahead and change that to a percentage. Just because in the real world percents make more sense. But you don't want to just say, oh, that's 26%. Still, let's keep some decimal places. So let's say that's about 25.92%. So it would be okay in your explanation if you had to write one up to say about 26% of runners have body weights that are less than 60 kilograms. And I did say that I would show real quick how I would do just do it a trick way. Let's see if it'll let me write a little bit thinner so I can fit it here. So then you could just skip the whole Z-score thing altogether. You would do normal CDF. You want to go from a big negative infinity. And so maybe do negative 1,000 or negative 100 or something like that to represent negative infinity up to the 60, and then 63.1 for our mean and 4.8 for our standard deviation. And you're going to see on the calculator over here that that's going to give us the same answer. Okay, so we would do negative a bigger number to represent negative infinity. And then we're going to do 60, 63.1 for the mean, and 4.8 for the standard deviation. So I know it gets kind of confusing of when do I leave the mean as 0 and 1, and when do I put in the real, the real mean and the real standard deviation of the data. And the deal is, are you dealing with a Z-score or are you dealing with an observed score? So when I did it the first time where I showed my work in red, I was using a Z-score. So then I use 0 and 1. But if I'm using 60, which is an observed score, then I want to use the true mean and the true standard deviation of our data set. But either way, you get the same answer. You have to go out 4 places before it's any different. So, and either one, when you round those 4 places, round to the same thing. So it doesn't hurt anything to check it with the trick, but please don't forget how to do a z-score because you're using the calculator to always find the area. That would not be good. So don't forget about your z-score. So we want to know what proportion now is above 70. So doing the z-score way, because I don't want us to forget how to do that. I'm going to say z is equal to observation minus mean over standard deviation, but now our observation is 70. So we're going to go 70 minus our mean of 63.1, and then our standard deviation is 4.8. And we should come up with a positive z-score this time because we are above the mean. And you need to start thinking about things like that so that if you come up with a wrong answer, then you're going to know, hey, that realistically doesn't make sense. So if you start thinking about what you're finding, you're going to catch mistakes, if you make them. So 70 minus 63.1 divided by 4.8 should give us a positive z-score, 1.4375. And we want to know what percentage of data, what proportion of data is above that z-score. So we want to do normal CDF again, but since we're going above, this is actually going to be our lower bound now. Before, when we had our z-score, remember that it represented our upper bound, but now it's going to represent our lower bound. Okay. So we're going to do normal CDF. That's going to be our lower bound, the 1.4375. We're going above it, and we're going to positive infinity. We're dealing with just z-score, so 10 is enough to represent positive infinity. We're going to do 0 for the mean and 1 for the standard deviation. Oh, sorry, wrong button. I want to do second VARS number 2. Normal CDF, so I'm doing 1.4375 as my z-score, my lower bound. And then I want to do 10 representing positive infinity as my upper bound, 0 for the mean, and 1 for the standard deviation. And so I have 0.0753. Okay, so that's about 7.53% if you want to change it to a percentage, which again kind of makes more sense if we had to discuss it and talk about it. And then the trick way of doing it instead, you would just go straight to normal CDF. You would not find a z-score. You would put 70 out to a big number representing positive infinity. You would put 63.1 for the mean, 4.8 for the standard deviation, and hopefully we'll get the exact same answer. So second VARS number 2, 70 for the lower, big number representing positive infinities. Remember, we're going above, so that's why we're doing, positive infinity. And then 63.1 for our mean, 4.8 for our standard deviation. And so you see we do get the same exact answer that time. Okay, part E, calculate and interpret the 45th percentile of the runner's body weight distribution. So now we have 45th percentile. Percentile means that's the area, that's the percentage, the area under the curve that's below whatever score we're talking about. So they want us to calculate and interpret that score. So we want to do inverse norm. And we actually want to do it of 0.45. If I do the inverse norm of 0.45, comma 0, comma 1, what that's going to give us is the z-score at that percentile. It's not going to give us the actual score or the actual weight in this scenario. It's going to give us the z-score, and I'll show you how to deal with that. So this gives us a z-score of negative 1257, and that's a z-score, okay? I'm going to write next to it, that's a z-score. Because I left the 0 and the 1 in, it gave me a z-score, not a true observed score. So we can take that z-score and remember that z is equal to observed minus mean over standard deviation. We're trying to find the observed score that has that as a z-score. So we know our z-score now is negative 0.1257. We don't know what the observed score is, so we're going to leave that as x, like our unknown, but we do know that the mean is 63.1, and we do know that the standard deviation is 4.8. So now I can just do some basic algebra and solve for x. So we want to take the negative 0.1257, multiply it by the 4.8, and then you want to add the 63.1, and that's going to tell me the actual weight that a person at the 45th percentile would be. Okay, so that gives us 62.4966. So we would say, and it does say interpret, so we would say that about 45% of runners are below a weight of about 62 kilograms, or let's do 62.5 because we don't want to lose, that much of the weight there. So about 45% of runners are below a weight of 62.5 kilograms would be a good interpretation of that. Okay, so now let's talk about the trick, trying to skip having to work anything out. We could just plug in the calculator initially from the inverse norm. We could have just done inverse norm of 0.45, putting in our true mean, and our true standard deviation should go straight to giving us the 62.5 and not even having to work out anything with the z-score formula. So I'm doing inverse norm, 0.45, but now I'm going to do a mean of 63.1 and a standard deviation of 4.8. Run it, and it should give me the 62.5 kilograms. So then you didn't have to do any of the work, but you did need to go ahead and still do that interpretation. Okay, number 2, find the proportion of observations from a standard normal distribution that satisfies z is greater than negative 1.51 and z is less than 0.84. Sketch the normal curve and shade the area under the curve. That is the answer to the question. I would actually probably start with the curve, just because I like to be able to visualize things. So I'm going to do our bell-shaped curve. We want to put, these are z-scores, so we're going to put 0 in the middle, and then we want to do our 1, 2, 3 on the right and 1, 2, 3 on the left. We have 1, 2, 3, negative 1, negative 2, negative 3. Again, those are representing our standard deviations, which are also our z-scores. Okay, and then we need to mark, the specific z-scores that they gave us. So negative 1.51 would be approximately in the, halfway point of negative 1 and negative 2. And then 0.84 would be pretty close to positive 1. And we want the area in between, so we want to shade the region in between. And so what I would do on the calculator is just do normal CDF. My lower bound is going to be the negative 1.51. My upper bound is going to be the 0.84. And we're dealing with z-scores, so we have a mean of 0 and a standard deviation of 1. So second bar is number 2, negative 1.51 for our lower bound. And then we have 0.84 for our upper bound, 0 for mean, 1 for standard deviation. Run it, and that's 0.7340. So what that is saying is that this area that we shaded is about 73.4%. So you just want to kind of look at it and make sure that makes sense. And then part B, what z-score in a normal distribution has 33% of all scores above it? If 33% of the scores are above it, then that means that 67% of the scores are below it, since we have 33% above, and it has to add to 100%. And so they want the z-score, so we're going to do inverse norm of 0.67, because when we do inverse norm, it's always talking about the area below the curve. Okay, so I'm going to do inverse norm of 0.67. Mean is 0, standard deviation is 1. Run it, and we get 0.4399. So let me write all that out for you. Inverse norm of 0.6701 equals 0.4399. When we do inverse norm, we are finding a z-score. We just found the z-score. You should not ever convert a z-score to percentage. It doesn't make sense. It wouldn't make sense to say, oh, this is about 44% standard deviations below the mean. Like, that doesn't make sense. So we just found a z-score. That's how many 0.4399. That's how many standard deviations we are below the mean. Okay, one more question, and this is the one I told you guys all you have to do is look, is, the scatter plot linear looking, and then so we would say, yes, it is normal. It is approximately normal because it's linear, and that's good enough. it is, we'll say roughly linear because it's not perfect, but it is close enough.